this word is closer to, these words are closer to each other, this word and this word are far apart. So by being able to understand that these words are related to each other, these ones are far apart, that's why we are able to generate text from machine. It's that's how we generate text. When we prompt at ChatGPT, it's like it's understanding what you're asking, then it's trying to see this word is connected with, even when it's generating text, it gives you something that makes a lot of sense, because it's able to figure out that these words are close to each other, and that's why I can form a sentence that says like this, and it is going to make sense, it's going to be grammatically correct, and so on. Yeah, so embedding is an important aspect of um, feature extraction in natural language processing. So we have several types of embeddings. For example, contextual, from the word context. So these are advanced embeddings where meaning of words depends on its sentence context. For example, bank in she sat on the river bank and he deposited money at the bank. These are two different sentences. When I say she sat on the river bank, that means she sat on the bank of a river. Then when somebody says he deposited money at the bank, we're not talking about the same banks. So that language is complicated. We can have one word mean different. And even sometimes one word, how it's spelled or how it's pronounced, how it's pronounced can mean differently, especially for African languages. You've seen that. So it's important to make a machine understand the context, you know. So traditional embeddings treat bank as the same in both cases, but that was before now we came up with the new technologies where we have contextual embeddings, like the machine is understanding the context of the sentence. That's why it's able to understand the sentiment, the mood, the tone, and so on. So contextual embeddings, that is just a type of NLP. We are going to learn more about GPTs and BAT. So if it sounds new, don't worry about it. We're going to learn it by the end of the topic. So like from this, treat them differently. Understanding the word changes meaning depending on the context. So as natural language processing evolve, we are able to make machines understand context. And from that, we're able to make machines understand maybe sentiment, maybe that's why sometimes it feels natural to talk to ChatGPT, because we have those advancements that have made it easy for a machine to understand what we mean, which context are we talking about, and even respond to that. Yeah, so it's called contextual embeddings. So also as part of feature extraction, we have syntactic features which relate to grammar. So how words are structured in a sentence, e.g. part of a speech. So it's whether a word is a noun, a verb, an adjective, we need to know. In pre-processing, in feature extraction, it's important for that machine to understand if this is a noun, how is it occurring in this sentence? What contribution is it making to the sentence? If it's a verb, is it in the past tense? Is it in the present tense? How is it changing the context of the sentence? So it's called syntactic features. We have semantic features. It's about meaning. So what words and phrases represent, e.g. named entities, identifying names of people, places, dates, etc. So semantic basically it's more about what the words mean, word meaning. So these are just several terms that we are used in for feature extraction. So that's why they're not like connecting to each other, but it's important for us to understand what they mean. So for example, knowing that automobile and car are similar. Sentiment, they are connected. Understanding if a sentence it's called polarity. Understanding if a sentence or a statement or a comment is positive or negative. Sentiment. And then we have another aspect called n-gram sequences. So it's a sequence of n consecutive words used to capture local context. For example, okay, n-grams help models understand short phrases or patterns for text prediction, spelling correction, language modeling, etc. So it's like n consecutive words from the word n consecutive words. How many consecutive words are we considering? Are we considering 5 consecutive words to form a meaning and so on? So the context is called n-gram sequences. So this is just like summary for feature extraction. So we have these are going to repeat themselves because it's a table that is helping us understand. So we have bag of words. So it counts word occurrences in a document, ignoring the order. So it's going to count how many words are there in. There's a new term I want you guys to. I think it's it has to have. I don't know if it has that R. I don't know where. Or no, not a corpse. Corpus. I need to. I think it's called corpus. I don't know, but when you're describing the text that you are feeding to a machine, when you're training a model in natural language processing, I think it's called corpus. I don't know. It has to be called that. Anyway, if I'm lying to you guys, you're going to correct me, please. It's called corpus. Yeah. So it's if you find it's just it describes that text. I have a text, or I have like just words, maybe a book, maybe just information. Yeah, information. So bag of words, it's counting the occurrence of a word in that corpus, in that information. So how many times does this word appear? Yeah. So we talked about term, frequency, inverse, IDF. It's going to count two-way words based on how important they are. But don't forget, we're also considering how rare that word occurs, because when we're going to assign weights based on how common words are, we can miss the context of the text. So this one assigns weights, but also this last part is responsible for focusing on rare words in that text. So we have word embeddings, is where we convert words into dense vectors based on meaning. So this is where we're able to convert text or words into a way that a machine can train on, because we need to, even I think we talked about machine learning, we talked about one hot encoding. We said that we need to convert our data into a way that a machine understands. So for natural language processing, this is called word embeddings. Yeah. So it can be character embedding, can be word, although character is not advisable, but most of the time you'll find word embeddings. But when you find character embeddings, it's still the same. So character embedding, it's like taking each character from the word, but that's not effective, because now it's like, when you separate a character, when I take this and separate the character, it becomes U-S-E-S. It's hard even for you as a person to find a meaning in character embedding. So word embedding is best preferred. So this is an output example for embeddings. Like it's giving it a vector, creating a relationship between that sentence and putting it in a vector. So we talked about contextual embeddings, where it's like now it's understanding the context. So instead of just doing embeddings and assigning vectors to the text, it's like trying to understand the context in that text when you're doing embeddings. Then we have parts of speech, name entity recognition. This is to it a part of speech extracts syntactic. And also for name entity recognition, we talked about something that identifies something or somebody, and so on. They are important parts of a text. Then we talked about n-grams, where it's extracting sequences of n words. When you talk about n, could be any number. This one is like a hyperparameter. Yeah. And then syntactic features, dependency relationship, tree depth. How are they connected? How are these words connected? So I don't know. Are we together up to there? Hello guys, any question? I need to know if you are together in peace, guys. I don't want to leave anybody behind. Or maybe you guys are ahead of me, so it's still okay. So are we together? I'll start mentioning names. So please, just unmute your mic and tell me if you're together. Or if you have any question, like before I proceed, are we okay so far?
Yes.
Okay. So that's all for feature extraction. Um, so we're going to learn more about different models that are used in natural language processing. Um, in the next subtopic, you're going to see like evolution of natural language processing and how it came to be up to right now. The way now we have a lot of, it's like we have natural language processing in everything, literally nowadays, in everything. But it has come from far. So we have the rule-based methods. This involves manually creating rules and hysterics to process language data. For example, defining patterns in language to extract meaning. So this is like rule-based. Um, I think originally we would store like words in like let's say a database, quotes and quotes database. And then we have several conditions. So it's like you're defining every rule. So for this one feels like coding. It's like coding NLP. It's like manual. So it's like you're not allowing um the machine to learn from data. So this is like the most original, but I don't think it's used anymore because nowadays we have those AI algorithm learning from data and everything. But now it's also important to understand you can do it rule based, defining all the conditions, you know. Yeah. And then we have now the second one, using machine learning and deep learning. So this involves using algorithms to automatically learn from data and improve over time. So we have machine learning and we have deep learning. So when you talk about machine learning, we're talking about using machine learning models. For example, logistic regression. This is for maybe for mostly it will be for text classification. Even before deep learning was like really started, we still had like things for like autocorrect. We still have those when you're typing in Microsoft Word, it's like the sentence is being finished for you. So it's like already when you type, it's like it's trying to predict what you're typing and then it's easy for you to finish. Spam filtering. So email spam was a big challenge like long time ago, but then people are still able to achieve spam filtering using machine learning. So yeah, we can use logistic regression, decision trees, naive bias, support vector machines, etc. These are like machine learning models to do natural language processing. But now we have deep learning. Now deep learning models are the ones that are enabling more things like creativity, text generation, uh, such things. For example, ChatGPT, I think it's the best example to use in this situation. So, deep learning models, we talked about recurrent neural networks. We say that they are mostly used for sequential data that is dependent on time, for example, videos, and also the sequential data, for example, text, because the first word will be connected to the last word in a text. Even if you're reading a book, those words are connected to each other. You can't process them individually. So it's still sequential data. And also, long short-term memory. This is a variation of recurrent neural network, and so is this gated recurrent unit. From even the word recurrent unit, it's also a variation of recurrent neural network. So like I think the recurrent neural network was like original, then it had some weaknesses like forgetting. It's called vanishing gradient. It's like it's forgetting because you're trying to train a model to connect the first word to the last word, the first video, the first second of the video to the last maybe hour of the video. So it had those problems. So improvements were done on it. That's why we have like long short-term memory networks. And then we have gated recurrent unit. Those are variations. But now we have another special one here called transformers. What are transformers? Transformers, they operate by, let me just quote and quote because I need you guys to do more research on this at your free time. It was a research paper called Attention is All. Attention is All. It's a very famous research paper which like explains how transformers operate. When I talk about transformers, ChatGPT is a transformer, is an example of a transformer. So what it does, it's like it tries to create relationship within. It's like it tries to understand the relationship and the context in a text. So a transformer is going to figure out this word is connected to this word, is connected to this word, and so on by just looking at the, it's like it's looking at the text in general. Like it's like the way you scan a book. Maybe when you see this page, you can just scan and pick the most important aspects of this page, the one that I'm sharing. That's how like a transformer it works, trying to scan a text and pick the important words and give. I think from the word attention. Anyways, I encourage you guys to read this paper. It's good. It shows how ChatGPT operates, but there's a lot that goes into creating something like ChatGPT to be what it is. Yeah, so yeah, transformers. And also, I think it's going to be explained in the next. Yeah, we're going to explain it more here when you're talking about encoders and decoders. Yeah, so that's like, yeah, these are different models that are used in natural language processing. So nowadays you'll find yourself using either machine learning or deep learning. Deep learning needs a lot of data, lots and lots of data. Machine learning can just use, whatever data you have. And also, as I said, it's about context. What data do you have? What are you trying to achieve with your model? So those, when you answer those two questions, it's when now you're going to determine which one am I going to use for this project. So they are dependent on data and the outcome. If you are trying to create something that is text generation, you're going to use deep learning. But if you're going to maybe to create something like just sentiment analysis, something that's just classifying things, you can consider using machine learning. And also, deep learning is hardware dependent. I think we talked about GPUs and TPUs. It's completely hardware dependent. So sometimes you can find yourself in a situation where you don't have enough resources to run like a deep learning model. So you can consider using a machine learning model. Machine learning models, they're okay. They're not as computer intensive as deep learning. So even for some the planning tasks, you'll find yourself maybe even for hackathons. I think I have done several hackathons whereby they give you computer resources, like they give you like GPUs because they understand that that hackathon is not possible without GPUs and so on. Yeah, so the planning is computer hardware, specifically hardware dependent. So all those factors affect the choice of algorithm that you're going to do in your project. So this is just a summary of we have a feature. Wait, we need to learn about space first. It's okay. We can learn more about the tools that are needed to do etc. But I think this slide should be the last one. Yeah, because we need to understand what is spacey. Uh, Already we know PyTorch and TensorFlow. I know you guys have used TensorFlow, but we have not used PyTorch for this coursework. But I said PyTorch is just like TensorFlow. It's another deep learning framework. Once you learn TensorFlow, it's easy to learn PyTorch, and vice versa. Once you learn PyTorch, it's easy to learn TensorFlow because they're like just they do the same work. So you can find yourself using TensorFlow and never using PyTorch, or maybe using PyTorch. But okay, for market and for because out there it's competitive, it's also important to learn all of them. But then when you're doing a project, there's no way you're going to use PyTorch and TensorFlow in the same project. You'll have to choose which one you're using, etc. So I think I'll come back to this slide after we've finished today's class. It will help us to understand more about what we've learned. Yeah. So we have let me call it library. It's a natural language processing library called Spacey. Is it a library? Okay, it's a library. So it's an open source software library for advanced natural language processing. So as I said, just like any other advancements in AI, natural language processing has come from way far. So we had the rule-based system, then we had this one. It's called Natural Language Toolkit. And then there has been a lot of improvements up to where we are right now. I can say like right now, natural language is like so good. It's so good. It's so accurate and so on. So there has been a lot of advancements in from where it began up to now. Yeah, so we have Space. It's an open source software library for advanced natural language processing. It includes components for named entity recognition, part of speech, the ones that we were talking about, parts of speech, tagging, dependency, sentence segmentation, text classification, lemmatization, morphological analysis, entity linking, and more. So it has a lot when it comes to NLP. And it's often preferred over natural language toolkit. So you can think of this one as like a rule-based one. For natural language toolkit, it's like it was useful. You can even find yourself using it right now when you're defining the rules. But then now Spacey, I don't know if it's spicy or spacey. I call it spacey. It's like an advanced version of natural language toolkit. So it has more things that are more automated as compared to this one. But then as we advance, you're going to realize like other things have come up. Yeah. So if you want to learn more about Spacey, I talked about documentation. If you want to understand well about these libraries, how they are used, what are their limitations, what are their improvements, and so on, I 100% recommend documentation. So when you go to Pandas documentation, go to NumPy documentation, go to Matplotlib, go to TensorFlow documentation, you're even going to learn how to install them, how to use them, how to run them in your local environment, in your online, in your virtual environment, and so on. So documentation is a key point in any tech. Honestly, if even you're doing any other thing in for the bootcamp, you're going to be told the same thing. Documentation. It's going to tell you everything you need to know. So this is documentation page for Spacey. So you can visit it and see what it does. But now we have small illustration, a small illustration. Now we have the text. So instead of doing all those pre-processing steps that we had mentioned, now they are like encompassed in a spacey, what do I call it? Let's say in spacey, this NLP aspect does all this for you, you know. So you have your text, then you pass it through NLP, everything is done, pre-processing, feature extraction, embeddings, etc. Now you have your output. So it's like simplifying the process. So any question so far? Are we good? So if you have a question, please don't hesitate to ask. Yeah, and also understand maybe you feel like you're learning a lot of things at once. That's okay, that's normal. But when you come and repeat this slide, it won't feel as new as when you're hearing it for the first time. Yeah, so it's about consistency. Yeah, so this is just another table to summarize for us data structure. When you talk about a document, a token, a span, a vocab, like seems like an advancement of vocab. So in NLP, we have like a lot of aspects. It's not as simple as computer vision, honestly, guys, because computer vision is just understanding that this is an RGB image. So if it's an RGB, I'm going to feed it to a convolutional neural network, then it's going to be flipped, done this and this. Then at the end of the day, my model is going to maybe classify or do an object detection. But now for NLP, it's it's more. We have like you're going to find a lot of new words, but we're all pointing to language, you know, because as we said, language is complicated. But now we want the computer to understand language and even to be able to generate. So yeah, it has to understand all these aspects. So doc is basically like a document, entire process text. These are like um I'll call them like these are like aspects of spacey also. You'll find yourself maybe using them when you're coding with spacey. Token is an individual token in a document or in a doc. A span is a slice of a doc, it's like a part of a doc. Vocab is like lexicon of known words, like vocabulary, vocab, you know, it's not as complicated. Then lexeme is a vocabulary entry for a word. So these are all connected. Like document is like looking at it at your information in its own entirety, like everything in that information. But now token is like we've talked about tokenization. We're trying to split our word, we're trying to understand the vocabulary because it's going to give us context. So this is just like small table that's showing us like the data structure. Especially when you're using space, you're going to use these words. Um, I'm not going to go through each and every word in this slide, but this has also like more things that you're going to use when you're using the spicy library. It's like a more explanation for example, for the project that you guys did for convolutional neural network, when you're dealing with TensorFlow, you have to say TF dot maybe whatever you want to do it. Maybe if you want to use like data that is already in TensorFlow frameworks, you can say TF dot data. You have some data sets that are like default data sets. Then if you want to do anything, if you want to convert something into tensor, because we had said that TensorFlow, its data type is called tensor. So you can say tf.tensor etc. So it's almost the same here. We are trying to access So you say NLP, get pipe, then it's the same. It's like, I don't want to get into it because I'm teaching you the code. So I don't think it makes a lot of sense. But yeah, this is just like a more summarization of maybe the most common attributes for spacing. So are we together? Hello guys. Are we together? Any questions so far? And don't just like, if you want me to repeat, I can still repeat. So guys, I want us to collaborate. Like, are we together? Is there something that you feel like I should repeat, or am I way behind? Like, you guys, I want us to communicate. So are we together? So I want to assume we are all together. So somebody has to unmute and tell me we're okay so that I proceed. Sharon, are we together?
Yes.
Okay. So this is a more explanation about now transformers. Transformer explains ChatGPT basically. So it's a deep learning model architecture introduced in the landmark paper 2017 called Attention is All You Need by this writer. It revolutionized the field of natural language processing. So it's just like a term. The way we have deep learning as a term, the way we have AI as a term. It's just like a term that maybe explains maybe how some deep learning models operate. So we have several concepts that define transformer. For example, self-attention. Each word or token looks at all other words in a sentence to decide what it should pay attention to. So, when you talk about a sentence, let's say I like AI. So this is just a simple sentence. It's like, instead of processing each token individually, it's like trying to look into the entire word, entire sentence, all the tokens, and try to see which one gives context to the sentence. This one could be maybe AI is the one that is giving context to the sentence, depending on you know what sentence we are looking at. We have positional encoding. Since transformers don't process input in order, they add a sense of position using vectors. So we talked about vectors, and I said machine learning, deep learning, AI, it's just math. It's not magic. It's just a way of manipulating math in a way that machines can learn from data and maybe you can get output. So when you talk about vectors, word vectors, um, if you get deeper into learning more about machine learning and even how those algorithms are formed, especially for deep learning, you're going to find it's all vectors, matrices, and so on. So it's like that's what computer understands, math. Anyway, so since transformers don't process inputs in order, they add sense of position using vectors. Then we have encoder decoder architecture. Encoder processes the input, decoder generates outputs. So when you talk about encoder and decoder, because even right now we have some models which are purely encoders, others are purely decoders, others are encoder decoder. So what does that mean? So encoder, think of an encoder as a listener. So it's like it takes input and tries to understand what it means. And then think of decoder as like a text generator or a speaker. So a decoder tries to generate text maybe in a way that is grammatically correct and has a valid meaning or something. So yeah, so some models can just be purely encoders trying to understand a text. Others are decoders trying to generate text. Others are encoder decoder. So an example of encoder decoder is maybe for Google translation. So maybe when I talk in Swahili, Google is trying that Google translator is going to understand my words in Swahili. Then that understanding itself is encoder. Then try to translate it into English. That translation into English, because maybe I wanted to translate it into English. It's like a decoder characteristics, you know, text generation, text output, and so on. So we have several models that are using maybe encoder only or decoder only or encoder decoder. And then we have another aspect such as parallel processing. So unlike recurrent neural networks, which go word by word, sequential data, transformers look at the whole sentence at once. As I said, it's like it's trying to scan and picking the most important. Well, attention, which words are catching your attention? That's how I think of it, though, by the way. Not entirely correct, but it helps me understand. So, trying to scan through the whole sentence, pick the most important words in that sentence, and so on. So, that is just an explanation of what transformers are and what they do, or how they work, not what they do, how they work. So, and encoder decoder model, I think I've already explained, but it's more to get like the more explanation on this. An encoder decoder model is used in machine learning tasks that involve sequences like translating sentences, generating text, or creating captions for images. So encoder takes the input sequence like sentences, and processes them, because we said an encoder is supposed to understand the text. I want you to understand what I'm saying, context, the syntax, the sentiment. It converts input into a fixed size summary called latent vector or context vector. This vector holds all the important information from the input sequence. Then decoder uses this summary to generate an output sequence, such as translated sentence. It is tries to reconstruct the desired output based on the encoded information. Yeah, so encoder is understanding, decoder is generating, trying to generate something that makes sense. An encoder decoder model, this is just let's say a diagram structure explaining the encoder side and the decoding side. But when we pay attention, you're going to realize it's everything that we've been learning. I know we haven't trained like a model from scratch, but we talked about feed forward network. We talked about back propagation. You know, we talked about pre-processing. We talked about softmax function, linear transformations. It's just the same thing. But now when you take that context and put it in a more complex model, you can find your model having different layers. In those layers, different things happen in those layers. This is just a pictorial representation of encoder decoder model. So several things that we have to understand. Input embeddings. We talked about embeddings. We said that we have a text. Then we need to convert that text into tokens. Then we need to convert those tokens into vectors. And then we need to assign maybe weights to those vectors, because it's going to help us, no, not us, help the machine understand the relationship between those tokens. Then we talked about positional encodings. They are added to input embeddings and they encode the position of each word in the sentence. Because also how the words are arranged in a sentence matters for context purposes. Does this verb come before a noun or after a noun? Is it trying to explain the noun? Or maybe sometimes sentences can be complicated. I know I'm using the simplest of all the sentences to give you example, but think of real world scenario where actually sentences are complicated. So that positional encoding, trying to see where each token fits in a sentence, is important. We have another aspect called multi-head attention. Multiple attention heads are applied in parallel. So we talked about parallel processing when we're talking about transformers. When you talk about parallel processing, it's like several things being processed at the same time, parallel processing. So that's like the simplest explanation for that. So when you talk about multi-head attention, we have multiple attention heads applied in parallel to process different parts of sequences simultaneously. So remember, when you talked about recurrent neural network, we said start with the first word of the paragraph or of the text or of the book or the website, whatever I'm getting my data from, then trying to read sequentially through the words or the text. But now, this attention concept, it's trying to scan the words. We're not trying to read them sequentially. So think of it that way, because when you are doing parallel processing, we're also trying to do many things at the same time, still saves on time. It's also important. So maybe if you have a long speech, we are trying to process different parts at the same time. So output of all attention heads is combined and passed for further preprocessing. So we have add and norm. We talked about normalization of data. So this layer helps in residual connection and layer normalization. This helps to avoid vanishing gradient problems and ensure stable training. So I know we've talked about vanishing gradients so much, but what is a vanishing gradient? Like simply explained. So we said that recurrent neural network experienced the problem of vanishing gradient. So it's where like there's too much information that when we're doing, we have like too many layers. We have too many layers. So sometimes when you are trying to do back propagation, when you talk about back propagation, I know we've talked about back propagation, but let's jog our memories. We said we have the feed forward network, then we have back propagation. When we're doing a feed forward network, we are doing a feed forward network, then we're going to evaluate the model. It's all part of training. Then we realize like, wow, the model is far from learning from data. Then we do a back propagation where we go and adjust the weights. So this back propagation is like you're going back to check where the error began. But now when you have too many layers, it's hard to trace back where the error began. So normalization solves that problem of vanishing gradient. So we have feed forward. Talked about feed forward. The first layer we feed to the second layer. The output of the next layer is the input of the next layer, the other layer. I think I drew like a simple network where like we have the input, maybe we have the hidden layer, then we have the output. So maybe this is the input, but the output of this hidden layer is going to be the input of the next hidden layer and so on. So that's called the feed forward mechanism. We have another aspect here called masked multi-head attention for the decoder. This is used in the decoder and ensures that each word can only attend to previous words in a sequence. So now we are doing encoder decoder. So encoder involves input embeddings, positional encoding, multi-head attention. We're doing normalization, and then we feed forward to the decoder. Assume this is a text translation model. So remember, an encoder understands the text. It's understanding what I'm saying, but a decoder generates the text. So now when we're generating, it's important to consider how words are connected to each other. We just don't want to just generate text for the sake of generating. It has to be grammatically correct. It has to make sense. So masked multi-head attention for decoder is used in decoder and ensures that each word can only attend to previous words in a sequence, not future words. So how ChatGPT works, for example, when you are generating, it is referring to the previous text before generating the next text, because we're trying to generate something that makes sense. I don't know if you are to get that there. And that's why we have another term called output embedding. Finally, transformed output is mapped to a final output space and processed by a softmax function to get output probabilities. So in as much as it seems easy, you prompt, you get a response, there's like a lot of, this layering that happens before a model gives you an output. But because it's like working in the background, you're going to just see the output. But sometimes chat even gives you options, response one, response two, then it's asking you which one is better, because we're still training these models. We're still telling them this is good, this is bad, and so on. But where we are at in NLP, right now we are so advanced. Even when it comes to voice processing, it's so advanced. Nowadays, you can just do everything with voice. It's just so easy. For those people who live in smart houses, you just get into the house, then you're like, oh, I need music. I need some dim lights. I need this playlist. I need do this, do this, do this. You can command your way around, and still your machine is the machine. When I talk about machine, anything that is machine that is trained with machine learning, I call it a machine. But then you see those smart homes, you can speak your way into stuff. Lights on, lights off, music on, music off, this on, this off, because nowadays natural language processing is so advanced. It's so advanced. But there's a lot of things that go to the background of, you know, training and everything to get those outputs. So are we together on the encoder decoder model? Like, any question? So yeah, we talked about Hugging Face. Say that when you want to maybe learn more about deep learning models, when you want to leverage our already pre-trained model, and you want to use your data to fine tune it. It's an open source. There's a lot of models, a lot. So it's a called Hugging Face. You can just go and visit and see what it has. It provides tools, libraries, and models for NLP and also computer vision and other machine learning tasks. It is best known for the Transformers library, which makes it easy to use state-of-the-art pre-trained model like BART, GPT, T5, Roberta. These are all different types of um, let's say NLP models, let's say technologies, quotes and quotes, that exist in the market. So yeah, when you are doing your deep learning project, Hugging Face is going to prove to be very useful, especially for deep learning, because as I said, deep learning is heavily dependent on data. The reason why we can't train for our project, the reason we can't train our own ChatGPT from scratch is because we don't even have the data, we don't even have the resources. We talked about the planning being computer intensive and so on. But now people have done that. People who have resources have pre-trained models for us where we can just go and leverage the pre-trained models to our needs. Yeah. So I think there's a slide that I had skipped earlier on. Now it takes me back here now. Mm, this does what do I say? A small explanation, like a table that's like summarizing like a lot of things. Uh when you're talking about pretend models, we're talking about deep learning integration, we're talking about multilingual support, we're talking about ease of use, community and ecosystem, best of use. Um, we're comparing Spacey and natural language toolkit and Hugging Face. So Spacey is available for NLP tasks, for example, name entity recognition, um, part of speech, etc. It supports PyTorch and TensorFlow. It includes 60 plus languages. FYI, when you talk about 60 plus languages, you have to realize like most African languages are not really translated. I think nowadays African data scientists are the ones now trying to train models using our own data. For example, if we have 54 tribes in Kenya, I don't know, 42 or 50 what, I don't know. Imagine all those languages. We still have like a long way to go when it comes to natural language processing, when it comes to making natural language useful for everyone. But so far, it's good. It's good. So far, so good. You know, a lot of advancements have been made. So space is simple, production focused. It has an active community. When you talk about community, when you experience a challenge in any of these Python libraries, pretty sure somebody else has experienced a similar challenge. So when you just go to the community and ask a question, you'll find answers. You'll find people who have gone through the same challenges and have been able to overcome the challenges. So when you talk about community, it makes it easy for projects, because when you can ask a question and get a response or get an answer, or maybe when you're stuck and the challenge has been solved, it becomes easy, when you're doing your personal projects. You won't get stuck. And now we have it is used for production NLP application. That's Spacey library. The natural language toolkit, it has limited pre-trained models. It has no direct integration with deep learning frameworks. It is limited and mainly English based. It's like a rule based, the way I said. Comprehensive but educational focus, strong academic community, educational purposes and research. So you won't find yourself using an LTK for production, but sometimes you can find yourself using it. As I said, everything in data depends on situation in the data that you have. Yeah. So I think that's why it calls for critical thinking, the analysis skills. That's why I think being a data scientist, being a data engineer, there's some data analysis in you, because you need to be analytical of the situation, the projects that I'm supposed to do. What is it that is needed? What is it that I have in terms of resources, in terms of data, and so on? But this one is not as, useful, because we have now advancements of NLTK, but then it's also good to know about it. Now we have Hugging Face. It has a lot of models, a lot of pre-trained models, seamless integration with PyTorch and TensorFlow. But that it's so open source that when you want to use a Hugging Face model, you just import it. It's so easy. You call the model, then you just use it in your data. So it's easy to use. A lot of multilingual models, high level APIs for deep learning. It has a huge community, model hub, collaboration, and then it's great because now it incorporates those new technologies for NLP, such as transformers. And if you want to fine tune, I talked about fine tuning. So fine tuning is where you already have your model that is already pre-trained. So you're not starting from scratch It's like now you're putting the last layer using your own data. Okay. So yeah, that's why I really needed to do this slide, the last one, because we've already covered all those things. But I think that's all. Um any question, or am I fast? Because I feel like I'm just moving. So I need feedback from you guys if we've understood today's lesson. So there was a small task on NLP, but we're not going to do this one, but I'll send it to you. I can also send the code for reference. Like if you're stuck, you can just okay. But my assignments already have their own code, so no pressure. Yeah, so I'll send you this assignment, which already has a code. It's going to help you understand more on natural language processing, but it's not the last assignment. So I, for balance purposes, we can't do this project and also do another project the same week. And I also want to finish the classes. So I'm trying not to overwhelm you guys, but also trying to give you as many resources as possible. Yeah. So any question? Um, I just need to hear from you guys. I feel like today I'm really, really, really speaking alone, and I don't want to speak alone. So any questions? Like, have you understood the topic? But also, I'll still insist. It's just you can't understand everything at once. But then you need to maybe learn and learn more and learn more. But also with all those resources that you already know, you're going to learn a lot. So it's also important to keep on upskilling. Like when the boot camp ends, please don't stop there. You're going to forget everything that you've learned. So don't forget that you've dedicated your time to learning, to growing. And also, this is a skill that is highly marketable at the moment. So, yes, Marianne.
I was asking about the assignments.
Mhm.
You're saying you're going to give us with the codes. So I was asking if at all we are restricted to using the codes you're going to give us, or we can also use maybe the codes that you're going to see, like the best suits and yeah.
No, you're not restricted. I think the reason I give you with the code is because like I don't want you to feel stuck. But then that's like a basic code. If you've noticed, like you can get as creative as possible with yourself. You don't even if you don't want to look at the code, don't just do your own stuff, achieve the goal. I think that is actually very impressive for me. Is that okay?
Yes, yes, it's okay.
Yeah, so you're not limited to the codes. I think the code has just guide you, because I also figured out like the boot camp was short. 8 weeks is short, and there's a lot that is needed to be learned in that period. So when I tell you guys go and find your own codes out there, it can be overwhelming. But then I think by now we have understood the flow. So if you go online, if you come up with your own code, I'm very supportive of that. In fact, that's what I want. I want you guys to come up with your own codes. Yes, Sharon.
I have a question on
Mm-hmm.
forward propagation.
Mm-hmm.
Do we train our model
Mm-hmm.
at that specific point, or after after that, then when we are doing the back propagation?
So forward propagation is all part of training model. So I because let's say we've already done that project for computer vision. So as you realize, when you feed the data, let's say you've already done the pre-processing, then you're feeding the data to the model. Maybe you can define several things. For example, the layers that you want the model to have. Then we also talked about hyperparameters, things that maybe the learning rate, the batch size. So what happens? The model is going to do a forward propagation, evaluate. Maybe you've said train like 10 epochs. It's going to do a forward propagation, then it's going to do a back propagation, then it's going to do another forward propagation until it achieves your hyperparameters. Now you can evaluate your model. So it already happens when the model is training, it's already doing a forward and back propagation. So it's not like something that we are doing ourselves, it's part of training the model. Have I answered your question?
Yes.
Yeah. Any other question? Okay, so I think if you don't have any more questions, I'll end the class there for today. So tomorrow we are going to learn more on RAG. RAG is called retrieval augmented generation. It's like maybe the last subtopic for NLP. As I said, NLP is advancing every day, so it's good to know those new technologies that are coming up and everything. And I'll also encourage you guys, because AI is evolving fast. It's also good to try to learn what is new in the market. Don't overwhelm yourself also, because upskilling can make you feel like you don't know anything, because you're always learning new things, trying to understand this, understand that. Don't get overwhelmed. Focus on progress. So as long as you're progressing, as long as today you have understood forward propagation, tomorrow you understand back propagation, that's enough progress. Don't put so much pressure on yourself, because eventually you're going to learn, eventually you're going to catch up to the speed. So yeah, that's all. We're going to learn RAG, then our final project will be based on RAG. So RAG is like an advancement of NLP, or maybe how we can now use NLP maybe for our mini projects. As I said, we can't train our own LLMs, but we can leverage the existing LLMs to maybe do business with, uh, maybe do a lot of stuff. Yeah, so that's all. Then maybe we finish the class on Thursday still on RAG. So it's also important for us to understand evolution of NLP, where we come from, also where we're heading. So it's also part of tomorrow's class. Yeah, then now Thursday we finish the class, then we do the project, then yeah, that's all. Any other question? So if we don't have any question, good night, guys. Keep learning, keep upskilling, and all the best in everything that you do, guys. Good night.
Good night.